Good morning, everyone. Welcome to class. Um, Today, my class will be more focused on the uh, deep neural network agent to make to represent the agent with deep neural network. There are two types of network in deep neural network agent. One of them was value-based DNN agent, which will predict state value function or action value function of the agent. Second type of DNN agent is called policy-based DNN agent. That will be the very core part of the class today. It will give us probabilistic distribution of your action and state, which will give you highest return. Especially, we're gonna talk more deeply into the reinforced algorithm and actor critic algorithm. In order to move on to this subject on policy value agent, I'd like to shortly review the overview of our class. Overview of our class is the deep reinforcement learning. And at the first part of our class, we was talking about the basic principles of deep learning. Especially it was called as machine learning. And in order to understand the basics of uh, machine learning, we studied many different models such as CNN, LSTM, GAN, transformer learning, and sometimes we studied the hybrid type of learning. And in particular, when we were talking about these models, we especially pay more attention to the back propagation through time, because the back propagation is the core part of the training process of this machine learning model. Second part of my class is now focused on the reinforcement learning. As you know, the reinforcement learning is very classical control theory. By combining this machine learning and reinforcement learning, we want to explore a new methodology, which I call it as deep reinforcement learning engineering. It may be very useful for optimal decision making, such as game, finance, and engineering. So this is very core part of our class. Now we both understanding basic principles of machine learning models and backpropagation. At the same time, we now know the classical control theory, which is called as reinforcement learning. And the core part of this deep reinforcement learning can be divided into two areas. One is value-based DNN agent, where deep neural network will represent the agent, and the agent, this DNN agent will give you the value of your action and state. Second type of approach is the policy-based DNN agent. This network will give you the probabilistic uh, probability of your state and action, which may give you highest value, action value or state value. So because this policy value-based DNN agent and policy-based DNN agent has different output, so probably because this is the deep neural network, we're gonna have different loss function and different backpropagation equations. Those will be the core part of our class today. And in particular, at the end of my class today, we're gonna little bit talk about actor critic, which combine both value-based DNN agent and policy-based DNN agent. Let us review a little bit about the class which we was talking about last Monday. That was the value-based DNN agent. As you remember that in reinforcement learning, we have agent, action, environment, reward, return, and state. So value-based DNN agent means that this agent will be represented by deep neural network. This is especially meaningful when the problem size is very large and model-free case. Model-free means we don't know what's going on inside. We just gain experience and predict the value. Based on those values, we can make optimal decisions. So in modern society, many problems such as games and engineering, I think the size is very large and we don't know the model very accurately. Sometimes we know that in engineering society, if you become expert in certain area, you know model very well. But computer itself does not understand what is inductance, capacitance, and transistors. But by training them, they itself will understand, even though language might be different, they may not think it is inductor or magnetic field or it is capacitor or electric field, but eventually they will learn the model. But the main target of DNN agent is that even though we are not teaching them the model of the engineering problem, they will learn itself uh, during the deep learning process. So in value-based DNN agent, this is the DNN, and I think most typical DNN network which can be used for reinforcement learning could be CNN type of network. And there might be convolution and pooling and fully connected layers. At the end, it will give you the classification of output. So input of the value-based DNN agent will be the state. If the, for example, it is a Go game, the state will be the position of white and black stones at each grid 19 by 19. Output will be the what would be next position of your stone, which will give you the highest return. So this network output will give you expected return. V means the expected return. To calculate this expected return, you need to know the probability of your state, or you have to gain experience using the Monte Carlo type of exploration. But if you know the exact probability of your state distribution, then it is called model-based case. Then you can calculate it. But in many cases, we don't know. So in order to calculate this value function, and the problem is very large, it is appropriate to use the deep neural network representation. Another type of output function is action value function, which give you the expected return as state as if you make an action. So basically, this output will give you the value. Value means the expected return, GT. Transition from expected return to actual value means that in model case, if you know the model, you can calculate using the model. If you do not know, Monte Carlo method or temporal difference method combined with Bellman equation will be used to calculate this value. Now, so you know if this is the CNN type of network, it is straightforward to calculate the forward propagation. I would say the activation function could be ReLU function. At the end of this fully connected layer, output function could be softmax type of function. So next step we have to do is we have to define the loss function to do the back propagation. So to apply the backpropagation, we need to know the loss function, plus we need to obtain the gradient of this loss function and softmax function and ReLU function. Softmax function in value-based network, it was defined by this equation. This equation means that this is the mean square error type of loss function. Here, with theta s is the output of this network. So in CNN, this V true means that this labeled the output, but we don't know. If you know the model, you can put it to calculate from the model. But if you do not know the model, that is the case of model-free case, you can obtain, maybe you assume that you can obtain the true value of the state value from Monte Carlo method or temporal difference method. So you have to generate the episode, and from the episode you can obtain the expected return. Our basic assumption is that the number of episodes is large enough, this return, your experience, is very close to the true value. So this difference of your experience and the output of your network at that different scale will be used as a loss function during the backpropagation. So there are two jobs you have to do when you are coding this reinforcement learning using a value-based agent. You have to obtain this true value of value function, and once you know that, you can obtain the loss function, and by applying the derivative loss function, you can go back propagation. And also, as a month before in the class, I show you some backpropagation chain rule equations in CNN. So those equations will be reused. So especially in a value-based DNN agent, we can, if you use the Monte Carlo method, you will obtain return from episode. In Monte Carlo simulation, you have to go to the end of the episode and you obtain GT. In AlphaGo game, you have to go to the end of the game, whether you win or lose. And that return has to be used as, if you win, your return will be 1. If you lose the game, your return will be -1. And this return will be used at true value. And because of this square nature, derivative of square is 2y dt dy. Derivative of this came here, and also you have to do the derivative of y with respect to t. That is exactly shown up on here. First term is this part, difference between your return minus your network output, and second term is the slope of this derivative. So there are two terms to update your network theta. This is the DNN parameters theta, and during the backpropagation we have to update this theta network parameter. This equation will be update equation, and because you have to minimize the loss, gradient distance means it has to go to the negative direction, minus, but because in derivative here we have minus here, that will come out, and then minus minus becomes a plus. So that's, we have plus here, still gradient descent. And so it has two terms when you are applying the backpropagation equation. First term is the difference between true number that will be obtained from Monte Carlo episode, and this is the network output. Second term is the gradient, slope, how fast, how slow. This slope will be multiplied to difference. So there are two terms, slope of this gradient and slope of the error term. This is the error term, and this is the slope of error. And these two are combined together to update your network parameters. So after many millions of forward propagation and back propagation, this DNN agent will become smarter and smarter. And at a point, this DNN agent will play Go game much better than human being. And how are we going to decide next position of your stone? You may choose a state action which will give you the highest value. In order to obtain this loss function, you have to explore your episode. How are we going to obtain the episode? You can play the game with a human like Isidore, or you can play with another DNN agent. This episode can be obtained between a machine learning agent with the human, or sometimes human, if is not good enough, machine learning agent and machine learning agent 2 will play together. And at the end of the game, you will have return, and that return will be used as a true value, and this loss function will be used to make a back propagation, and you will update this network. And after millions of games, computer can do that very easily in a second. Then you can train this network, and train this agent will make very good decision, probably much smarter than human being. That is the approach of value-based network. Basically, value-based network has an output of state value function or action value function. That's why we are using this type of loss function. There are other type of value-based DNN agent. Sometimes if your episode is non-terminating episode, so you cannot go up to the end. So you just play a game one step, and you obtain the update return, and that will be used. We believe this is the true value, and the difference between true value and your output, I mean your network output, will be used to update the network parameters. That is called temporal difference method. The other useful method being used in Atari game is called deep Q-learning. In this case, we are not specifying certain action. We just try many different actions, and among the action we choose the highest value, and that will be used as a true number. And still, this is the action still value. Q means the still value with the network output as state S and state A. Especially in Q learning, instead of small q, we are using capital Q. And here again, we are playing it by using this method. What the advantage of this work is that we can use the multi-agent. For example, if one machine learning is playing game, second one is playing game, thousands of the machine learning model can play the Go game. Among them, we choose the highest action, and that value function will be used as a true value. I think this deep Q learning is very useful because we can use multi-agent or multi-computing power to find the best action to give us highest value. But number one, Monte Carlo method, temporal difference method, and Q-learning, still the basic idea is the same. We are using the mean square error type loss function, and that is being used as a backpropagation chain rule. And the only difference is how are we going to obtain true value. Sometimes you are using the Monte Carlo method, sometimes using temporal difference method, sometimes we are using the multi-agent. And we gather all the experience together to update this network. That is called deep Q-learning. Now, so far, I was talking about value-based DNN agent. Second type of DNN agent, so the basic idea is that agent is replaced by deep neural network. Deep neural network has network parameter and models. If we represent agent with the deep neural network, we have two different type of approach. One is the value-based agent, this which I just discussed before. In this deep neural network, output is the value function. Value itself. So once you train this value-based DNN agent, you can make a best action based on these values. You choose the highest value function. And Q-learning, we are using the capital Q, and still it is a value function. And in the Q-learning method, we can use many different episodes in parallel. But still, the output of this deep neural network is the value. Meanwhile, now I would like to talk about policy-based DNN agent that is described by pi theta. Pi theta means, let's assume that you have a state S. If you make an action, the probability of your winning game. So it is a probability of highest return. So it is the value, it is probability. So because this is value and probability, loss function and backpropagation and gradient, backpropagation and gradient are little bit different. Not much different, but little bit different. And there's only a little bit difference between those two. So sometimes if you are developing deep reinforcement learning program, sometimes you can use value-based DNN agent or policy-based DNN agent. I don't know which one is better. Probably depending on applications, sometimes value-based agent may work better, sometimes policy-based DNN agent may be better. Value output means that, let's assume you are developing stock investment reinforcement learning software. If that is based on value-based DNN agent, it will give you expected gain of your money if you invest certain money into the certain company. But policy-based network, it doesn't give you how much money you gain. It gives you the highest probability of state or action, which give you the highest return. So those are different. So in policy-based network, the output will give you the probability distribution of states and action. And if I'm a decision maker. I would like to choose a state and action which give you the highest probability. Third type of DNN agent is called actor critic. Here, there are two agents are working together. Actor agent will be policy-based network, and critic agent will be uh, modeled by based value-based DNN agent. So initially, you design certain policy, and upon certain policy, you train the network, policy network. Once you have this policy, you can calculate the value, and value will criticize your actor. If this value network is not good enough, it will give you the feedback, and you will train this network iteratively, value network and policy network. Those are called actor critic. These are the overview of class. Now, I'd like to go into policy-based DNN agent. So this is a comparison between the two, value-based agent and policy-based agent. As I said that policy-based neural network agent is described by pi theta mathematically. It will be used for model-free case and large size. Input will be the state, output will be the probabilistic distribution pi theta SA. In policy-based agent network, we are going to use this target function to update your network. Here, in value-based neural network, we use the mean square error type of function, and to minimize this error, we use the back propagation. So this kind of function is called loss function, and we would like to minimize the loss, so we use gradient descent method when you are training the network parameter f theta. But here, our target, we are not going to use the loss function. Here we are going to use the target function. Target function is defined by this equation. Now I would like to explain the difference between the value-based agent network and the policy-based network agent. And first difference is that value-based network give us value, but policy-based network give us probabilistic distribution. That's the first difference. Second difference is that when we are training the value-based network, we are using the mean square error type loss function. But however, in policy-based agent network, we are using the target network. Those are second difference. Now, how are we going to understand a target function? Target function is ds is the probability of your state as state. This is probability. This is the expected value as state. So here, target function is expected value. So in order to obtain this target, you have to know this probability while you are staying at S, and also you have to know the value function when you are at state S. Both we don't know. In the actor critic type of network, we can obtain this value from value-based agent network. But anyway, This is our target. So because we will train this policy-based network to maximize this target. As much as you have higher value, and that is our target of the reinforcement learning. So in this case, we will train this target function to maximize. Here, we will train the network to minimize the loss. Minimize the loss. That's called gradient descent method. Here, we want to maximize the target. So we're going to use gradient descent method. We're going to train the theta to minimize the loss. But here, we're going to train this network to maximize the target. Those are the difference between value-based agent network or policy-based agent network. I personally, in mathematical point of view, either you can use value-based agent network or policy-based agent network. But philosophy to reach the optimal point seems to be a little bit different. So now I assume that you know very well about value-based agent network. Now I would like to move a little bit further into policy-based agent network. Number one, I would like to say is that it will be useful for model-free, very large case. Second is that the output is the probability distribution of your highest return. And third one is will be we're gonna define the target function. Target function is the expected your return, and we are involved in the probability here. And number four is we're gonna train the theta network parameter of this network to maximize the target. So because of that, we're gonna use the gradient ascent method. So I think this is the, again, same type of, I already mentioned before, so I'm gonna move on to next step. So this will be very difficult part of the machine, the policy-based network. Please pay attention to this. I told you that policy network is we have to define the target function, and then we have to maximize this target function, and during that maximization, we will obtain the optimal network parameter. As I mentioned in the previous slide, cost function is multiplication of your probability of state S multiplied by value function at state S, expected value function. Then you have to summarize all the states. So if you are playing the grid game, you have to add all the possibility of each position. Each position of your next stone will be the state, and you're gonna add all the possible return multiplied by your stone is there, that probability. And then this expected return can be replaced by this summation. That means that probability of your state and action and return at that state and action. And you have to summarize all the actions. So probability distribution are included twice in this target function. First term is your probability at state S, and the second probability is your state action A at state S. So as I mentioned before, because this is model, if this is a model-based case, we know this probability of your state, your probability of your action. And this probability of action will be given from your DNN network in Polish-based DNN network in Polish-based neural network agent. But in model-free case, we don't know. So the only way we can obtain this probability of your state and action is you gain the experience. How are we going to gain the experience? We can do the Monte Carlo type of tree exploration. At the end of the class, I'm going to give you a little bit about Monte Carlo tree search method being used in Go game, AlphaGo game. Now, our real target is to obtain this gradient of your target function. Once you obtain the gradient of your target function, we will apply that into the gradient authentication. So simply you do again and again million times, you will obtain your network parameter, and your network parameter will give you the best smart network, which will give you the very smart decision. In order to do that, we have to obtain the gradient of your target function. And target function is the expected return, total return. This is really total return, total expected return for all state and action. So target function is all the probability distribution multiplied by return. So that's because of the state distribution and action distribution. And now next step is we would like to obtain the gradient of this target function, and we apply the gradient operation here. I would like to remind you that gradient means the derivative of certain function with respect x, y, z. So it's a kind of vectorial distributions. So scalar function, derivative or gradient of scalar function usually give the vector function. So this is gradient operator, and gradient is done only by network parameter theta. And so this distribution of your state, and we assume, and is not a function of your network parameter, and your network parameter is only affecting this DNN agent. This gives you the probability distribution as state S with the action A. And so operator, gradient operator will move into this summation symbol. So you only do the gradient of your network. To make a more easy job during the Monte Carlo sampling, we're gonna do some mathematical operations. We will add this new term, pi theta is denominator, and also same pi theta is added at the numerator. So this equation and this equations are same. Now this numerator will move into inside. So we're gonna obtain these two terms because numerator and denominators are same. Mathematically, it is identical. And interesting is that this first term is remained. Second term is rewritten as a form of log function, because derivative of log function is, I say, derivative of log function is become 1 minus 1 divided by y. So derivative of log function is becoming the same function is appears on the numerator, and second and denominator we have to apply the differentiation. This is a little bit not useful, but if you have a college student in engineering mathematics, derivative of log function will be changed to this term. So now it's more likely becoming entropic type of function because of log function. And now what does that mean is that we have first term is the probability distribution, and second term is probability distribution. Third term is the slope, a gradient. Fourth term is return. But we don't know number one, number two, because this is model-free case. So what I would like to say is that this is the highlight of our class today. The derivative of this target function can be obtained using this equation, the second term. First term is kind of probability distribution of your state and probability of your distribution of your action A. But we don't know because this is model-free case, but we can get some sampling using the Monte Carlo type of approach. And if the number of those sampling are good enough, large enough, we assume that is true value. So the very core part of policy-based network backpropagation is that you sample this part, you do the sampling of this part, gradient of log of your network output plus multiplied by your experience of your return. You obtain that from Monte Carlo method or temporal difference method. You do the many times, you average it, and it is being used during the backpropagation, this gradient. That is the core part of this policy-based network. Now I'd like to go back again here. Let me summarize the comparison between value-based agent network and policy-based agent network. Once again, I would like to summarize that in here, agent in reinforcement learning will be replaced by neural network, deep neural network. And the value-based agent network is gonna give us the value, and we're gonna use this mean square error type of loss function and during the backpropagation. And this true value, network true value, will be obtained during the Monte Carlo type of exploration or episode. But in policy-based network, we are defining the target function, which is the total value function of expected value of your whole state and action. So you're gonna train this network to maximize this target function. So here, in order to calculate this expected value for all state and action, we have to know the probability of state and action and probability of state. And those are to be trained in this network. So how are we going to obtain this target function? We're gonna use this equation that we will obtain this gradient of log pi theta, that is the network output of log. And if this is CNN type of network, we have to do the log operation of softmax function and also ReLU function. So you will obtain this return at the end of your episode. And if you do the many episodes using the Monte Carlo tree sort, we assume that that is expected real value, and that is the gradient of your target function, and that will be used in when you are doing the update of backpropagation. That is the core part of the policy-based function. And in Monte Carlo method, we're gonna use this Q value, that is the state value function, state action function, action value function at state and S. You have to go to the end of episode to obtain this one, and we can use this gradient to update. In one step or one step MDP, you just move one step. Sometimes you just move one step and you obtain the return that will be used to maximize this target function. So there might be some different type of in Monte Carlo process, you have to go up to the end of the game. Sometimes, depending on your model or application, you just move one step and you obtain the new reward, and that will be used into the gradient descent. But the important thing is that this log part of your network output and gradient will be the very core part of the backpropagation and during the gradient ascent process. And why we have log part, I think this is because of probabilic nature of this policy network. These are some experiences, especially if you go to the end of the episode using the Monte Carlo method, that is called reinforce. That this is basically policy based agent, DNN agent, and we use the Monte Carlo method, and we are gonna use the return. Here we are going to use the return, but first part is the same, gradient of log part of the policy network output. This is the output of the network, and this second part of the during the sampling, how are we going to do that? We have to go to the end of the episode, and if you apply these three, then we call that model, the deep reinforcement learning model is we usually call de-enforce, capital. We are using the capital letter. Let's assume that at the end of AlphaGo game, let's assume that you lost the game, then return will be 1. If you lost the game, return will be -1. So this will be become plus, this will becomes minus. So somehow theta should be upgraded into the increasing direction. In return is -1, you have to update this parameter into the decreasing direction. So depending on at the end of episode, whether you win the game or lose the game, training direction of your network parameter will be opposite direction. In policy-based deep neural network, let's assume that if your return is 1, you will gradually increase the network parameters. But if your gain is 100, very large, you will increase this network parameter very rapidly. So this term, gradient of log of network will be the same, but depending on your gain at the end of episode, whether it is 1, -1, or 1 or 100, your direction of your training update of your network parameter theta and the speed of your increasing or decreasing of your network parameter will be different. Lastly, I would like to give you an example to talk about actor critic. This is another type of policy network combined. Here we have two parts. First part of a target function will be obtained from uh, from like a reinforcement law pre-policy-based network, and we're gonna use the target function, and we're gonna update this network parameter, and at the time we're going to use this gradient ascent equation. On the other hand, we have second part in the reinforced algorithm, as I discussed before. This can be obtained at the up to the end of the episode. But another method is that we can represent this QW with also DNN network, value network. We assume that here network parameter is theta, here we assume network parameter is W. Because second part is the policy network or value network, we're gonna use the gradient descent method, and that is this equation. This is gradient descent equation being used in value-based network. First part can be obtained from policy network. Once again, I would like to say that in actor critic network, we have two parts to be obtained, and this will be used as a gradient of your network target function. Depending on this gradient target function, we're gonna update theta and W. And two terms are represented by policy network and value network. And so we have to, during the backpropagation, we'll have two different workload. One is the policy network backpropagation and value network backpropagation. And during the policy network backpropagation, we're gonna use this gradient authentication. And during the backpropagation of value-based network, we're gonna use the value gradient descent equation. I think uh, this part is the very core part of our class. In order to understand really, we have to accumulate all the knowledges and understanding and mathematics to discuss it. But I'm sure that most of your students will have good idea about the actor critic, which I'm talking about right now. In other graph, I would like to explain once again. In actor critic, we are going to use the two network together. One is the policy-based network. Policy-based network will give you the probability distribution, and value network will give us the expected value distribution. We're gonna train both together, and by doing that together, we can eventually find the optimal solution. And the policy-based network will be trained using this gradient authentication, where we have gradient of log function, that is the probabilistic nature of the network. And in the second network is value-based network, where we will define the mean square function, and derivative of mean square function has the two terms. And during the Monte Carlo type of experience, we will gather this true value that will be used to update this network parameter at value-based network. This is the end of a class for policy-based deep neural network agent. Now, I would like to talk a little bit about Monte Carlo tree search. So many times in our class, I said that during the training, we need to develop episode. So the episode means that it is a way we can gain experience. So how are we going to generate this episode? Episode generation. There might be many different type of episode generation. It could be totally random, or it could be you can design a new episode based on your previous experiences or previous policy network or previous value network. So depending on different policy applications, this kind of episode generation will be very important part of your reinforcement learning. Whether you can generate randomly or you can use the previous experiences. I think there are, this is the graphical description of Monte Carlo tree search being used in AlphaGo game. Initially, you start state S and you make an action. It is a kind of a Go game. Then, depending on the opponent player's game, you design then you move into the next state, and then you make an action, and then you will move on to next state, and you make an action, and so state, action will continue. Maybe the number of cases could be 10 to 6 different cases or million or billion cases. So you have to gather or generate the episode up to the end of the game, and eventually you will obtain the return. So once you obtain the return, you will go back action and state and action and state and action and state and action and state. You will go back propagation. During those back propagation, you use this type of equation, back propagation equation, to update your parameters. At each position of state and action, at that position, you can calculate this return, and at those points, you can also calculate network output, gradient of your network output, because this will be represented by CNN. During the CNN, logo of softmax output or ReLU function is mathematically possible. So gradient of this log output of CNN can be obtained mathematically, and also you can get at each state and action, you can obtain this value. So at each state of action, you can update these network parameters. So during the Monte Carlo tree search, there are two back propagation. You go through back state action through action, that is the opposite direction of your Markov decision process. Second back propagation is at each state and action, you can update your network parameters. I think in Monte Carlo tree search, there are two back propagation. One is you go back, and then you update your return. And once you update the return, you can update network parameters. So now, next step, how are you going to generate next episode? You can move up to the same tree. At the end, you can move on to the different tree, or at the beginning, you can move on to different tree. But what I would like to suggest is 99% you go your previous experience, who has given you plus winning reward, and probably 1% you will try different episode. So this episode generation is also very important type of reinforcement learning. So maybe we can, if I become an AI engineer, here we have two different policy-based network and value-based network. I may design a new network, say tree network, to generate what kind of episode we're gonna generate. But this type of value network and backpropagation tree, it takes a lot of computation. That's why we need to use the GPU and multiple GPU. Thousands or millions GPUs are needed because we have to try this many different type of episode, not only once, many times. And we do not need to only focus on one tree. We have to try many, investigate some different, some low probability trees, because sometimes we may miss some important trees. So because of that, we come back to again the significance of computing power. This is very short summary of Monte Carlo tree search to generate the episode and backpropagation being used during the AlphaGo game. But once again, if I give you a summary of class, we have policy network and value network. And because this is model free, we do not know probabilities. So what I assume is that if we try many different type of Monte Carlo tree search, if those number of trees are more than million or billion, I assume that is true value. And we update this, educate this policy network or value network using those kind of Monte Carlo tree search episode. And because value network give us a value, we're gonna use the mean square error type of loss function. But target of policy give us the probability of state and action, which give us highest value. So because of probability nature, we will define the target value will be the expected return. And because of expected return type of probability nature, we will define different type of target function, and we're gonna use the different type of gradient ascent method. Now, at the middle of our class, we mentioned a little bit about the keywords in deep reinforcement learning. And one of the target of my class is that you understanding basic concepts of these keywords so that you can combine this with deep neural network. Let's check one by one. Now we know what is action. Joungho, I saw your face there. You know what the action is, I'm sure. Do you? It is not easy. It is not difficult concept. Now we know reward. Reward is very important concept in Monte Carlo Markov decision process. That is very key. So depending on how you define reward, your network will have different direction of optimization. And return is also important. This is total reward, and we will add all the reward up to the end of episode. So return is gonna be used to educate policy network or value network. To obtain this return, you have to go to the up to the end of episode, or sometimes you move a couple of steps. And even though you move a couple of steps, still you can update the return because we can use the Bellman equation. And we know what is state, we know what is discount factor, we know what is the environment. And agent, today's our class is more very focused on we talked a lot about agent. Agent can be represented by this table, equations, or many methods, but in our class, this will be represented by deep neural network, and there are policy network, value network, and actor critic network. In order to update to reach the optimal point, and one method we used is the loop cycle that is called dynamic programming that came from computing power. And we know also value is expected return. expected means we need to know model or model free. And also, once we know the value, we can design the policy. Policy is the action plan, probability of your action. This is the expected value. Sometimes we know model, sometimes we do not model. Model free is more useful in network agent. We know that what is the Markov decision process requirement, and calculating the value network is called uh, prediction, and designing this policy is called control. This prediction and control is combining together to give you a planning. And when you are making the planning, you are deciding your action. Sometimes we have to have design the action which give us highest value function. That is called greedy action. And during the Bellman equation, we use the state value function and action value function and Polish function. Polish function is the action probability, and Q pi is the action value function is the expected value at state S when you are making action A, and state value function is the expected return at state S. And please remind yourself that a month before we didn't know anything about this. Now we can freely talking about that. And especially in deep neural network, we represent this agent using the value network, Polish network. And especially in gradient descent method, we define the target function. And mathematically, we use the gradient of log function. And those are being used in gradient descent method. So in order to obtain the true value or true theta value, we don't know. So in model free case, so we have to use the Monte Carlo type of method. And sometimes if the episode is non-terminating, we can use the different temporal difference method. We talked a little bit about Q-learning. That is one of the value network. Also today we talked a little bit about the policy network. One of them was the reinforced, and by combining value network and policy network, we was able to talk about actor critic model today. In order to generate the episode, I briefly mentioned about Monte Carlo tree search, which was used in AlphaGo game. And during the Monte Carlo tree search, there are 4 processes: selection, expansion, simulation, and backpropagation. And I mentioned we have 2 types of backpropagation in Monte Carlo tree search. Those are the end of my class today, and thank you for your kind attention. I think today's class is mathematically most complicated one, but if you look back again this lecture notes or textbook, you will have much easier time to understand. And I hope that when you are developing your own models or codings, these basics will really help you to do much more job. Thank you.